In the last lecture we discussed the basic mechanism of polarization of a dielectric medium, and we saw that in the case of a gaseous dielectric, gases, so we have the relation epsilon minus 1 equal to n alpha. This is known as the Clausius equation. Here epsilon is the relative dielectric constant, n is the number of dipoles, atomic or molecular dipoles per meter cube, and alpha is the polarizability. We also saw that when we come to a condensed phase like a solid or a liquid, we saw that this equation is not valid anymore because of the presence of a local field which is not equal to the applied electric field, because of the presence of an internal field which is also known as the Lorentz field. So, it is this E local which has to be used here in this equation, and this leads to a modification of the Clausius equation in the form and this is known as the Clausius-Mosotty equation. And this is what is valid for solids and liquid dielectrics. So, this is the Clausius-Mosotty equation which has to be used for solid and liquid dielectric, and therefore of relevance to us. Since we also know that the dielectric constant is proportional to n square from EM theory, we can also write this as in this form. This is known as the Lorentz relation. So, if you measure the refractive index n, this is the refractive index. You can use this equation at optical frequencies. So, this is the overall situation, and we also saw how when we go from the static to the dynamic situation where the applied field is a function of omega, the frequency. So, it is an alternating field, for example an AC field, then you have the frequency dependent dielectric constant, which is basically because of the polarization of various entities in the medium. The mechanism of polarizations can be of different kinds: electronic, ionic, and dipolar or orientational. Last time we discussed these with a specific reference to examples such as sodium chloride and water and so on. Sodium chloride is an ionic material, and the ionic contribution will not be able to keep pace, will not be able to follow the fast frequency variations of the applied electric field, and therefore, it will not contribute to the polarization at high frequencies. Whereas, the electronic polarization will go all the way, will be able to follow, the polarization follows the field variations right up to the ultraviolet across the visible spectrum. And for example, if you have a polar molecule like water, in which there is a permanent electric dipole moment, then there is an orientation of these dipoles in the applied electric field, and this also has a certain time constant, and therefore, depending on the relaxation of these dipoles, this will also contribute only up to a certain frequency, such as microwaves. So, this is what we saw last time, and all these three together are illustrated in the next figure, where we have plotted the polarizability as a function of frequency. Now, what we see is that at low frequencies you have the dipolar mechanism. So, you have something like this. So, the epsilon omega as a function of omega starts from this static value and goes down, and then there is a region here, and then there is a region here. So, that is the overall shape of the polarizability as a function of frequency. So, this is the dipolar region, dipolar relaxation, this is the ionic, and this is the electronic. So, that is the overall behavior of the polarizability, and we will consider these in some detail next. So, let us consider electronic polarization. So, we have a medium in which there are bound electrons. The electrons are not free in a dielectric, like unlike in a metal. So, they are bound electrons. So, when the electric field is acts upon them, the electrons are only slightly displaced by the electric field. So, first let us see how this polarizability may be calculated in the static case. So, this can be done because we have already seen how in the presence of an applied electric field, in the case of a spherical atom, the electronic cloud with the nucleus in the presence of an applied electric field, how the nucleus gets displaced slightly, while the electronic cloud is displaced much more, and so there is a rigid shift of this electronic cloud. So, the centers of positive and negative charges are displaced relative to each other, say by an amount x. So, now we can use Gauss theorem to calculate the polarizability, because Gauss theorem says that is the flux due to an electric field, and that is equal to the charge, which is minus E is the electronic charge, times x cube by a cube, because in both cases it will be 4/3 pi x cube and 4/3 pi a cube. I am writing 4/3 pi cancels off, and this is all we are left with. So, that we have E x equal to 4 pi epsilon naught a cube E. and this is what we call the dipole moment, induced dipole moment. And therefore, we can see from the definition of the polarizability that the polarizability alpha is 4 pi a cube. So, it is proportional to the atomic volume. This is of course in the static situation, but when there is a time dependent or a oscillating electric field, the response of the electron, a given electron, can be written using the equation of motion, which is m d square x by dt square, that is the mass times the acceleration by Newton's law, plus b times dx by dt. This is because the electronic motion always experiences a resistance for its motion, and this resistive force per unit mass is taken to be proportional to the speed or velocity. Then the bound electron has, it is bound with a kind of elastically or to the atom with a kind of force which can be represented in the simple approximation, the simplest model, by a harmonic oscillator of natural frequency x omega naught. So, that I can write omega naught square x equal to minus e to the power I omega t. So, that is the equation of motion which has to be solved, and we assume, since I am writing only the time dependence here. So, I also assume that the displacement also has a form e to the power I omega t. So, that there might be a phase shift, but we will just consider this. So, omega naught square here is just k by m, where k is the time force constant. So, using this we can immediately write m omega square plus b omega I plus omega naught square times x naught equal to minus e naught. So, that x can be written, x naught can be written as well, we will write b by m as b. We will just define this by the damping per unit mass. So, that we simply are left with this. So, immediately we can calculate the dipole moment, because the dipole moment in this case is minus E x naught, that is the amplitude of the oscillating dipole moment, and therefore, this will be and since we have the dipole moment, the total polarization is just n times p. So, this is p naught, and therefore, this will simply be n e square by m e naught by omega naught square minus omega square plus I b omega. And therefore, since the relation between this is what gives you the epsilon. So, so this can be written as epsilon minus 1. So, that we get the dielectric constant, and because of this factor I here, this becomes a complex quantity, and therefore, the epsilon is in general complex. So, let us write it as epsilon prime plus I epsilon double prime. So, we have a complex dielectric constant. So, the real and imaginary parts are there. So, it can be separated into real and imaginary parts, and we have these are plotted here. They are given, the real and imaginary parts are given in the equation here, and therefore, you can see that they are plotted here, the real and imaginary parts of the dielectric constant as a function of frequency. So, the real and imaginary parts look like this. So, if I take epsilon prime omega as a function of frequency in the neighborhood of a resonance, then I have something like so that is the kind of response. So, this is the real part of the dielectric constant, while the imaginary part will look so. So, these two are the same. So, the imaginary part has a maximum. So, this is what is known as a Lorentzian shape. We call this the dispersive part, and this is the absorption. So, dispersion and absorption. The real part of the dielectric constant is associated with dispersion, while the imaginary part of the dielectric constant is related to the absorption. Now, we saw that there are several other mechanisms. We will not consider the ionic in detail now. We will instead go to the other case where there are permanent dipoles in the system. So, the medium, the dielectric medium is what is called a polar dielectric. For example, water has a large dipole moment. So, if you have a polar dielectric, this means that there are permanent electric dipole moments. As distinct from induced electric dipoles, which persist only as long as there is an applied electric field. For example, some typical substances are water, carbon dioxide, so hydrogen chloride, chloroform, etc. They are all highly polar dielectrics. So, what happens is that these dipoles tend to orient themselves, in an applied field. So, it is this orientation which gives you the polarization in these cases, because if they orient more, as they orient more and more, like get aligned along the electric field, there is the polarization increases. Now, this orientation tendency is opposed by the thermal energy. The system has thermal energy which tends to restore the disorder, which tends to thermal energy is always leads to disorder the dipoles. So, there is an ordering influence due to the applied field, and which competes with the disordering influence. The equilibrium polarization at any given temperature at a given temperature. That is what determines the dielectric constant. So, this can be easily calculated, and this is a temperature dependent process, unlike the induced dipole mechanism, the electronic or ionic mechanism. So, this is a temperature dependent, because the thermal energy is more. So, there is a temperature dependence for the orientational polarizability. So, this is how the orientational contribution to the polarizability can be separated from the electronic or ionic contribution, because you measure the dielectric constant as a function of temperature at different temperatures, and then the temperature dependent part comes from the orientational mechanism. So, let us consider this mechanism. We have, let us write down what is the polarization. The polarization is P, it is a thermal average, statistical average, which is n times the individual average of the individual dipole moment, where this average P is integral P cos theta. This is the projection of the dipole moment of the permanent dipole in the direction of the applied field times this is the usual Maxwell-Boltzmann factor, statistical factor, times df cos theta . 0 to pi, 0 to 1, minus 1 to 1 to minus 1. Exponential P e cos theta by k b t times df cos theta. Now, this can be evaluated, you get this as this is the functional dependence. This function is usually known as the Langevin function. L of A. Now, A is P e by k b t. For A tending to 0, that is P e by k b t tends to 0, that is in small applied fields or at very high temperatures, P goes to P square by 3 k b t times E. So, the orientational polarizability is just P square by 3 k b t, and therefore, the total polarization is P equals. So, that gives the orientational polarization as of, and it has an inverse temperature dependence for the absolute temperature T. So, you have a dielectric susceptibility which varies inversely with the temperature, unlike the electronic and ionic contributions. So, if you measure the dielectric constant as a function of temperature and plot it as a versus 1 by T, you will get a straight line for the orientational contribution, which may therefore be separated. Now, this alignment which we talked about, this equilibrium alignment of the dipoles is not of course an instantaneous process and is governed by a relaxation time. So, there is a time dependent polarization which is due to the alignment of these dipoles. This time dependence can be written in terms of the time dependence of the polarization can be written as P equilibrium minus P by tau, where tau is a characteristic relaxation time for the dipoles to get aligned, and P equilibrium is the equilibrium polarization. So, if you have this, we can write this as I omega P, therefore, this gives you a rate equation which is P equal to P equilibrium by 1 minus I omega tau, and so 1 plus, and this is P equilibrium to 1 minus I omega tau by 1 plus omega square tau square. So, again you can see that the equilibrium polarization is complex and therefore, the relative dielectric constant due to this mechanism is also a complex quantity. Again, the real part of which is the dispersive part, and the imaginary part is the absorption. So, this is the contribution which we showed in the figure. We now come to a very important related concept, namely that of ferroelectric phase transition. We talked at the beginning of this lecture course about thermodynamic phase transitions, such as the gas to liquid transition and then the liquid to solid phase transitions. We are going to talk about another kind of phase transition which takes place in dielectric materials, which is known as the ferroelectric phase transition. So, this is an important class of phase transitions which takes the material from a paraelectric to a ferroelectric. Paraelectric to a ferroelectric phase at low temperatures. For example, barium titanate is a very well known ferroelectric material which has a ferroelectric phase transition temperature in the neighborhood of 120 degrees Celsius. So, below 120 degrees Celsius it is ferroelectric, above this it is a paraelectric. What do you mean by a ferroelectric material? A ferroelectric material is characterized by the existence of what is known as a spontaneous polarization. There is a spontaneous polarization. Normally, till now we have been talking about situations where an applied electric field tends to create a polarization, induce a polarization, or orient the dipoles to produce a polarization, net polarization. So, here this is an entirely different situation where even in the absence of an applied electric field there is a polarization. A polarization is present even when there is no applied electric field. So, it is called spontaneous polarization. Ferroelectrics are materials which are characterized by the existence of a spontaneous polarization, whereas a paraelectric is one in which there is no spontaneous polarization and you need an applied electric field in order to create a polarization. Now, this ferroelectric behavior may be qualitatively understood from the Clausius-Mossotti relationship. Now, if you take this, we have something like so this, let us recall this, this is the form of Clausius-Mossotti relation, and look at, if we look at the denominator, this denominator will become 0 when n alpha equal to 3. Then this becomes 0 and therefore, the dielectric constant is singular, it blows up. So, this means there would be a non-zero polarization even when the field is 0. This is known as the polarization catastrophe, where the dielectric constant, the polarization blows up and goes to infinity because of this behavior. So, when this condition is met. So, this behavior is illustrated in the next picture, where the ferroelectric phase transition is shown in barium titanate at 120 Celsius. So, there is a polarization catastrophe. So, above the transition temperature of 120 degrees Celsius, barium titanate exists in the cubic phase. The structure is a cubic structure which is known as the perovskite structure. above, whereas once you cool it below 120 degrees Celsius, there is a structural phase transition. The structure, the crystal structure changes along with the ferroelectric phase transition, and this becomes a tetragonal structure. Below 120 Celsius. So, and then subsequently it becomes a monoclinic and rhombohedral. So, this is shown in this picture. The cubic perovskite structure of barium titanate is shown in the figure. This is the structure of the barium titanate. The titanium ions are at the center of this cubic cell and surrounded by an octahedron of oxygen atoms, and then the barium atoms occupy the corners of this cube. So, this is the structure at high temperatures, but once you cool below 120 Celsius, this goes into a tetragonal structure, because the titanium ion, which is at the body center of the cubic unit cell, gets displaced, and because of this displacement there is a spontaneous polarization. This is the mechanism of the build up of the spontaneous polarization in this ferroelectric. Now, the general features of a ferroelectric phase transition may be understood in terms of the Landau theory of phase transitions. The general approach of Landau theory is to define an order parameter. So, this is the crucial feature of the Landau theory of phase transitions. Define an order parameter. The order parameter can be any physical quantity which is 0 for above the transition temperature and non-zero below. So, that is the general definition of the order parameter. In this present case of a ferroelectric material, the order parameter is the spontaneous polarization. Obviously, there is no spontaneous polarization above Tc, the transition temperature, and the spontaneous polarization exists and therefore is non-zero below Tc. So, that is the order parameter in this case. The next step in the Landau theory, which is a thermodynamic theory. This thermodynamic theory always says, why should there be a phase transition? The phase transition takes place and the change, there is a change in phase, in this case the structural phase and therefore the ferroelectric phase, because of a lowering of the free energy. Below Tc. So, the free energy becomes lowered in the ordered phase, and therefore, this lowering of the free energy favors the existence of the ordered phase over the disordered phase. So, that is the basic explanation, thermodynamic explanation given by the Landau theory. So, how do you find this? So, you expand the free energy in powers of the order parameter, in this case the spontaneous polarization. So, we write this is Gibbs free energy G, which is written as G naught plus alpha p plus beta by 2 p square plus etcetera. p square, p to the power 4, etc. Terms in p, p cube, etc. do not exist because this has such a ferroelectric state as a center of symmetry, and therefore, odd powers will vanish under the operation of the center of inversion. Therefore, only even powers p square, p to the power 4, etc. are there. Alpha, beta are constants which have to be determined by the minimization of the free energy. So, the entire exercise is to minimize this free energy with respect to variations in the order parameter. Changes in P. So, if I do that, this is the free energy difference, and this is minimized by taking the differential coefficient with respect to P, and that will be alpha plus alpha P plus beta P cube, neglecting the higher order terms plus etc., which are neglected. So, this is the derivative of the free energy difference with respect to P, and we set this equal to 0 for a minimum. This gives me alpha equal to minus beta P square, or P square is minus alpha by beta. So, the minimum is characterized by a spontaneous polarization which is minus alpha by beta. So, this is the order parameter. So, we expect it to be 0 above T c and non-zero below T c. So, in order that this should happen and P will be real, so P square should be a positive definite quantity. Therefore, we take alpha to be less than 0 for T less than T c. Alpha is negative, so that minus alpha by beta is positive when beta is also positive. And the corresponding free energy difference, when we substitute this, delta G equals G minus G naught equal to alpha P plus beta by 2 alpha P square plus beta by 2 P to the power 4, and substituting P square equal to minus alpha by beta for the minimization condition, we get this to be alpha times minus alpha or mod alpha by beta plus beta by 2 into alpha square by beta square. So, this gives me alpha square by beta minus plus, yes. So, this will be, I can write this as alpha by 2 into minus alpha. So, this becomes minus alpha square plus alpha square by 2 beta, which gives me minus alpha square by. So, one can see that there is a reduction in the free energy below T c. So, the free energy is lower, we expect, provided beta is positive, and alpha now can be taken to be a function of T. So, alpha can be written as alpha naught times T minus T c, it is a linear function of the temperature. So, we take this to be a alpha changes sign at T c and become positive, making the paraelectric phase energetically more stable at higher temperatures. So, the simplest analytical form is this, and therefore, we have P equal to 0 for T equal to T c and P equal to 0 for T greater than T c and equal to plus minus mod alpha by beta for T less than T c to the power half, taking square root for P square. So, the Landau theory thus predicts a spontaneous polarization which goes as alpha to the power half or P goes as T minus T c or T c minus T to the power half. So, that is the temperature dependence predicted by the Landau theory for the spontaneous polarization. And above T c, the dielectric susceptibility goes as T greater than T c, the susceptibility goes as 2 alpha naught into T c T minus T c, as you can check readily. So, this is the temperature dependence for the susceptibility above the phase transition, and this is the temperature dependence predicted for the spontaneous temperature dependence for the spontaneous polarization below T c. So, these are features which have been verified. Ferroelectric compounds in general fall into three main classes. One is the perovskites such as the barium titanate which we have discussed. Then there is another family which is called the Rochelle salt type of compounds, and then a third class for which the prototype is the potassium dihydrogen phosphate type known as hydrogen bonded ferroelectrics. Dielectrics in which adjacent dipoles are lined up not parallel to each other as in this case, but anti-parallel to each other also exhibit a sharp discontinuity in the relative dielectric constant at a transition temperature. These are known as anti-ferroelectrics. In the next lecture, we will consider piezoelectrics, another important class of dielectric materials.